Hello everyone, I'm Javier and this is the Electronic Component Basics workshop. So a little overview for this workshop. I'll be going over a background on some of the important electrical components we used throughout the exhibit. Starting off with LEDs. LED stands for light emitting diode, and what they do is convert electricity into light. This electricity flows in one direction from the anode of the LED to its cathode. The anode is a positive leg, labeled red in this picture, and it is a longer leg, which connects to the power source. The cathode is the negative leg and connects to the ground. Resistors are important when working with LEDs, as they limit the amount of electrical current flowing in a circuit, preventing damage to the LEDs and other electrical components. They're color-coded based on their resistance, and since this code is universal and based on a global standard, if you're not sure of the resistance of a resistor, you could just look up online based on its color to find out. In order to understand how to use resistors, it's important to understand the concepts of current, voltage, and resistance. Current is a measure of the amount of charged particles passing a point per unit time. Most of the time, it's the flow of electrons, but can be anything with an electrical charge, like protons or ions. Voltage is the distance in potential energy, or difference in potential energy per unit charge between 2 points. Voltage can be thought of as pressure on the wire, with current as the flow. So with higher voltage, there is a higher current. This is because, similar to how air particles in high pressure areas move towards low pressure areas, electrons in areas with high potential energy move towards a low potential energy, and this movement causes current. And the higher the difference between the high and low areas, the harder the particles will move towards the low area. Resistance is a property of materials that resists current. And similar to friction, everything has a resistance. Ohm's law describes the relationship between these three properties. It states that voltage over resistance equals current. This is a very useful proportion when working with electrical components because after you determine the voltages throughout your system, based on whether your components are in series or in parallel, you can figure out how much resistance is needed to output a specific current. This is important because all electrical components have specifications for how much current they can safely handle. You can find these specifications on their data sheets, but for the standard LEDs that we used, they can usually handle between 15 to 30 milliamps. Once you calculate the voltage of a circuit, and you know the current specifications of your electrical components, all you need to do is plug the voltage and current into Ohm's law, and you'll know how much resistance is needed to run the current through the components safely. Moving on, wires are obviously a very important part of any circuit. There are many different types of wires, and their properties, as well as the environment they are used in, dictate the safety and performance of a circuit. The main properties I'll be going over are stranded versus solid wires, the gauge of a wire, and its insulation. Choosing the right wire depends on the situation, but for the most part in this exhibit it hasn't really mattered since we used pretty low voltages. Stranded wires are made up of many thin wires, and because of that they're a lot more flexible and bendable than solid wires, so they're good to use with moving parts. However, they're also more difficult for through-hole soldering and have to be tinned before doing so. On the other hand, solid wires are more stiff and brittle, so they're easier to solder onto a breadboard. Gauge is the measure of thickness of the conducting part of the wire. The lower the gauge, the thicker the wire. And the thicker the wire, the more heat it can carry without overheating. You can usually find the gauge written on the insulation part of the wire, as written in white in this picture. There are also ampacity charts, which show the maximum current a wire with a certain gauge can carry safely. These charts differ based on the material of the wire, so if you ever use one, just make sure it matches the material of your wire. Finally, insulation is a protective coat around the wire. It can be many different materials, each performing differently based on things like the environment, the temperature, and the voltage of the circuit. The insulation prevents wires from touching each other and shorting, as well as protects the wires from environmental damage. Moving on to breadboards, they're used for connecting electrical components together to make a circuit. There are two main categories. One is the plastic breadboard, which is just a grid of holes with spring-loaded clips to insert wires and components into the holes without soldering. And they're used for making temporary connections that can be easily inserted and removed. So they're good for prototyping, testing, and debugging a circuit before it's finalized. Prototype breadboard is a grid of copper or any other type of conductive metal-lined holes used to form connections through soldering. These are used if you have a finalized circuit you already tested and are ready to make. They're much more durable and used for the final circuit that you want to implement. All circuits require a power supply. And when choosing a power supply, it is important to consider the project requirements, whether it's the voltage required by the circuit, the combined maximum current drawn by all of its components, or how portable you want the circuit to be. For example, if you know the circuit will be near an outlet, a wall power supply could work, but if you want it to be more portable, you're probably going to want a battery-powered power supply. When working on the exhibit, the power supply we had oftentimes didn't match the voltage needed for the circuit. So that's where voltage regulators come in. They're devices used to maintain a constant output voltage, and they're helpful if your power supply voltage is too high or too low, or if you just need a more stable voltage output. There are two main categories. One is a linear regulator, which steps down the voltage to a constant value, and the other is the switching regulators, which can be used to step up or step down the voltage. So linear regulators are smaller and simpler components and should be used when you want a small voltage drop like 5 volts to 3 volts, or just a low cost and simple implementation on your circuit. Switching regulators are used for larger differences in voltages and can also raise the voltage in addition to lowering the voltage. And they're also good if you want higher efficiency in your circuit. You can also use a combination of the two, using switching for the initial voltage change, and then using linear regulators for getting voltages for specific devices. One type of switched regulator commonly used in the exhibit was a buck converter, which can be used to step down the output voltage. To insert the converter into a circuit, you have to solder the power supply's voltage output into in positive and its ground into in negative. Then solder a wire from out positive to where the voltage is needed and out negative to the circuit's ground. To control how much voltage is outputted, turn the screw on the blue box using a screwdriver to adjust the value, and use a voltmeter to continuously check its voltage until it's at its desired level. Thank you all for listening, and I hope you learned a little bit more about some of the electronic components used in the exhibit.